Today, the goal is to provide a really nice visual intuition behind the formula for integration by parts. As you can see, we're going to start simply with this blue rectangle, and we're going to represent the side lengths of this rectangle with the variables u and v. We're going to say that the variables u and v are dependent on the input variable of x, so that by changing the value of x, the side lengths u and v of the rectangle also change accordingly. We're also going to choose to label the area of our rectangle as the letter y, so that way at any point in time we can calculate our area y by doing the base times the height, or u times v. Now we are going to do something that is a hallmark of calculus-related scenarios, and we're going to analyze what happens when we increase the value of x by some infinitely tiny amount, which we'll denote as dx. We find that in increasing the value of x by some really small amount, the values of u and v also increase by their own infinitely small amounts, which we'll label as du and dv, and as a result, the area of the rectangle itself increases by its own really tiny amount, which we'll label as dy. If we want to calculate this change to our area, dy, we'll have to do this by adding up the areas of our new rectangles that have been tacked on to our original blue rectangle. Each of these areas can be calculated by doing their base times their height, resulting in u times dv plus v times du plus du times dv. Because everything here is drawn way bigger than it should be for demonstration purposes, we need to remember that these rectangles are all existing as baby slices with infinitely small widths. And as such, our little green rectangle has both an infinitely small base and height. So the area of our little green rectangle is so unbelievably small that it is actually negligible to our calculation. This means that dy is actually equal to just u times dv plus v times du. At this point, this equation that we've set up can be manipulated in two different ways, so that it can be used to find the product rule for finding derivatives, or the method of integration by parts for finding integrals. In this video, I'll be deriving the method of integration by parts, but if you'd also like to learn where the product rule for derivatives comes from, you can go watch my other video on that. In manipulating this equation, we know from algebra that if we apply the same operation to everything on both sides of the equation, then the equation will still remain true. We're going to take advantage of this and integrate everything on both sides. Now, recall that this term on the left side of the equation is just saying add up infinitely many, infinitely small pieces of y, which is simply equal to y. Also recall, as we defined at the beginning of this video, that y is the area of our rectangle, and therefore equal to u times v. Now we can rearrange this equation by subtracting the integral of v times du from both sides, and we find that the integral of u times dv is equal to u times v minus the integral of v times du. This formula right here is often referred to as the formula for integration by parts, and is extremely useful for integrating a scary-looking function that can be broken up into two separate pieces, one that is easily differentiated and one that is easily integrated. The theory behind integration by parts is that in performing these calculations, you can transform the scary-looking integral into an expression involving a new integral that is much less scary.